Welcome to the set of Calc 101, Continuity and Discontinuity, take 384.
Today's class, we will cover continuity and discontinuity. This lesson covers the definition of continuity, how to tell if a function is continuous or discontinuous, and identifying points of continuity and discontinuity. This is the definition of continuity. A function f is continuous at a number a if the limit of f of x as x approaches a is equal to f of a. This requires that f of a is defined. This means that a must be contained within the domain of the function. Also, the limit of f of x as x approaches a must exist, and the limit of f of x as x approaches a must be equal to f of a. Okay, class, here's an example of a straight line. Hope, do you think this is continuous or discontinuous?
Continuous.
You are right, and you want to know why? All straight lines are continuous. Those are in fact the only thing that are continuous. Here's another example. This is discontinuous because, like I just said, only straight lines are continuous, nothing like this with all the twists and turns.
Whoa, cut. Do you even know what you're doing? You're not even following the definition of continuity.
If this movie is going to be a success, then we need someone who knows what we're doing. We need to bring an expert in. I'm the expert! I can teach you about discontinuity and continuity so your movie will be great.
Many functions can be continuous, not only straight lines. As long as there are no jumps, skips, holes, or asymptotes in a graph, a function is continuous. In addition, graphs can be continuous at some points while being discontinuous at other points. This function is discontinuous at x equals 0 because there is an asymptote at x equals 0. However, the function is continuous from both the left and the right when approaching 0. When we get very close to 0 from the left, both the limit of the function and the output of the function equal negative infinity. Therefore, this agrees with the definition of continuity. In addition, when we get very close to 0 from the right, we see the same results. Both the output of the function and the limit as we approach 0 from the right equal infinity, this time positive. So this again agrees with the definition of continuity, as the definition states that the limit of the function as x approaches a is equal to the output of the function at a.
This means that the function is continuous on the open interval of negative infinity to 0 union 0 to infinity.
In this example, there is a hole. A hole occurs when there are common factors in both the numerator and the denominator. In this problem, both x plus 2 and x plus 2 are in the numerator and the denominator. So in order to find the discontinuity, we set these equal to 0. Discontinuity occurs at negative 2.
This means that the function is continuous on the open interval of negative infinity to negative 2 union negative 2 to infinity.
So I hope that I've helped you and your movie will be a success. I think people will be able to learn calculus now that you've shown us how to deal with continuity and discontinuity.
Let's get back to filming our movie.
426.
Let's do an example, class. So here we have a piecewise defined function. F of x equals x plus 3 if x is less than or equal to 0, and f of x equals x if x is greater than 0. So first, we're going to graph this. I'll graph the part of f of x equals x plus 3 first. This is only when x is less than or equal to 0, so I'll start at 0. There is a y-intercept of positive 3. and an x-intercept of negative 3. And then there's a slope of 1. So this part of the graph looks like that. The other part of the graph just has a positive slope of 1 going through the origin. However, this is only true when x is greater than 0. So there's a hole in the graph at 0 for this part of the function. Then there's a positive slope of 1. Now class, is this function continuous or discontinuous? Mariah?
It is not continuous because there's a jump in the graph at x equals 0.
Good job. So, the function is discontinuous at x equals 0. And that is your final answer. Now let's try another example. Let's try the absolute value function. F of x equals the absolute value of x. So first, let's graph this. We all know that this function looks like a V. I'll plot a few points first and then connect them. Now class, is this function continuous or discontinuous? What do you think, Hope?
I think that it's continuous because there are no jumps, holes, skips, or asymptotes.
Very good. This is continuous.
This means that the function is continuous on the open interval of negative infinity to infinity.
Now class, it's your turn. Try this one. F of x equals x cubed minus 5 over x minus 2.
For this function, we don't even need to graph it. The top is continuous because it's a cubic, and we know it won't have any holes, jumps, skips, or asymptotes. In this example, we need to be concerned about the denominator and where it equals 0. Where the denominator equals 0, there will be a hole in the graph. To find where the hole is located on the graph, set the denominator equal to 0 and solve. So x minus 2 equals 0. Add the 2 over to solve for x. X equals 2. There is a hole located. Therefore, we know that the graph is discontinuous at x equals 2. And that is your final answer.
Now, this is a really tricky problem, so I'm going to hand it over to my best student, Hope. It says, sketch the graph of a function that is continuous everywhere except at x equals 3, and is continuous from the left at x equals 3. Go ahead.
For this example, we are going to sketch the graph following the guidelines. Because the guidelines say that the function is continuous everywhere except at x equals 3, we know that there is something happening at this x value that makes the function discontinuous. As we read further, we realize that it is continuous from the left but not from the right, meaning that there is a jump in the graph. Because the function is continuous from the left, it means that there is a closed circle here. But because it is discontinuous from the right, it means that there is an open circle here. There are many different possibilities of what this graph could look like as long as there is an open circle when x approaches 3 from the right and a closed circle when x approaches 3 from the left.
Now class, you're going to try a piecewise defined function in a group of 2.
Be my partner, Hopi!
Yeah, Mariah!
You should find where this graph is discontinuous and continuous. F of x equals x plus 1 if x is less than or equal to 1. F of x equals 1 over x if x is greater than 1 but less than 3. When x is greater than or equal to 3, f of x is the square root of x minus 3.
First, we are going to graph the three functions without worrying about the restrictions. For x plus 1, there is a y-intercept at 1 and an x-intercept at negative 1. The function also has a slope of 1. When graphing 1 over x, make sure it passes through 1, 1 because it's an important point to pay attention to when graphing the function. For square root of x minus 3, graph the function, the square root of x, shifted to the right 3 units. Now we need to go back to the restrictions. F of x equals x plus 1 only when x is less than or equal to 1, so we need to erase all parts to the right of 1, with a closed circle at 1. F of x equals 1 over x only when x is between 1 and 3, so we must have open circles at each of these values and erase the parts of 1 over x to the right and left of these values. When graphing the square root of x minus 3, there must be a closed circle at 3, and we don't need to worry about erasing anything because the function f of x equals the square root of x minus 3 is already undefined to the left of 3.
Now we need to talk about the continuity and discontinuity of the function. The function is discontinuous at x equals 3 and x equals 1 because there are skips in the graph at these values. The function is continuous from the right at x equals 3 because there is a closed circle when approaching the value from the right. The function is continuous from the left at x equals 1 because there is a closed circle when approaching the value from the left. These are your final answers.
This means that the function is continuous on the following interval: parenthesis negative infinity, comma 1 bracket, union parenthesis 1, comma 3, parenthesis, union bracket 3, comma infinity. In conclusion, you can tell if a function is continuous or discontinuous by graphing or looking at the equation and identifying holes, jumps, skips, and asymptotes. In order to be continuous at any point, the limit of f of x as x approaches a must be equal to f of a. A function could be discontinuous at x equals a if a is not in the domain of f, the limit doesn't exist, or the limit and the output of the function are not equal. A function is discontinuous whenever there is a jump, skip, hole, or asymptote. Don't forget, many functions are continuous, not just straight lines. Also, functions can be continuous at some points and discontinuous at others.
Do you think this is continuous or discontinuous? We all know that the absolute value function looks like a V. Shoot.
The graph is discontinuous.
Because all straight lines are
Go!
f of x equals x minus x.
Intercept at x equal, or wait, how do I say it? Will you type this part, please? My brain hurts.